Hello, 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 one and all, wherever you are. Right, this question, as it says there, look, is on shear strain. And all shear strain is when something is in shear. So when you rip a bit of paper, that's shear strain and shear stress. Right, so I put shear strain and stress by that. So it's very similar to tensile or compression, it's just a different direction. So here's our question. So we've got, this could be like a block, a rubber block or something like that. Rubber, for example, a little block. And it's like sitting on this bit of metal or something, I don't know. Okay, so I'll put not to scale here because before somebody says not, right? Not to scale. So this rubber block is 200 mil length that way. It's 30 mil high. And it's 55 mil going backwards into that, backwards into the page type thing. Okay, and it's fixed, so it's fixed there, so it can't slip or can't move. Okay, just bonded or glued or okay. And then on the top here, it's got a force. This orange thing here, there's like a 90 kilonewton force pulling it from the top. Now that force is trying to, it would try and shear this block. Okay, so it's a little bit of rubber being sheared, right? And if you can imagine it, if that force is allowed to do what it does, that block, right, I'll just get a pen here. That block, I'll exaggerate it, right? That block might go, let's get a different color. Go for blue. That block might do this, right? So it'll go sort of on the slant like that. Because that force there, this 90 kilonewtons force, has sort of skewed it across. Okay, it's now in shear. See, obviously, if it wasn't fixed here, it would just move, right? But it's starting to deform a bit, right? Now, in our example, let's pretend that this deformation, look, that squint bit, right? Because it was straight there, look. Now it's in shear. So let's pretend that that force makes this block deform by 0.8 of a millimeters. Okay. So, right, so we're pretending now that, so that's still 200, nothing's changing here. Okay. The height of it, we will still assume is 30. Okay, and it's going back 55 mil. But this sort of deformation there, that squint there, that, where it's gone on the squint, is 0.8 of a millimeter. So it's in shear, and that shear stress, that shear force of 90 has caused that deformation of 0.8 millimeters. Okay. So in this question, we've got to find shear stress. Right? Shear stress, because it's in shear. Okay, it's not in tension or compression, it's in shear. So we've got to find shear stress and we've got to find shear strain. Okay. Stress and strain, just like we've done sort of before. Right? Shear stress and shear strain. This block is in shear. That's why we're doing shear stress and shear strain. Okay. So number one will be shear stress, number two will be shear strain. So number one is going to be shear stress. Shear stress coming up. So shear stress. Now shear stress is just the stress due to shear. And we all know, different color, okay, that stress is force divided by area. Okay. we can still use that formula. Okay, so if you want to, you can put shear stress there if you want to. But stress, as we know, is force divided by area. Okay, and if I go up, I know that it's 90 kilonewtons is the force, and the area is this area in here, look. So it's the area that, what's going on here? It's the area in there, look. So it's like the area that this rubber block is attached to the floor type thing, right? So it's that cross-sectional area. It's not the, this area here, it's the area there. So if you can see it, it's like the area that is stuck to the floor. That square or that rectangle. And if you can see, it's going to be 200, because that's 200, look. 200, and then we've got this 55 coming back there. So it's going to be 200 times by 55. Obviously, we've got to be in meters, so we'll convert these to meters in a bit. Okay, so the area is that bit of the rubber block that's stuck to the floor type thing. Right? So it's that square there. Look, it's getting messy now. Look, right? But it's 200 times by 55. That's the area, and the force is 90,000. Okay. Now, the area has got to be in meters squared. All right. So it was, what do we say? It was 0.2 times by 0.055. That's right, isn't it? Yeah, because 200. So that's 0.2, because we've got to be in meters. So I'm dividing 200 divided by 1,000, because there's 1,000 millimeters in a meter. And then if you divide 55 by 1,000, because we've got to be in meters, okay, 0.055, okay, because we've got to be in newtons and we've got to be in meters. So the area's got to be in meters squared. Don't leave it in millimeters squared or inches, right? So that's the area. And we know the force is, what's the force? 90,000. Okay. So I'm going to do 90. It's kilonewtons, so it's 90,000. Okay, or on your calculator, you could do that. Look, 90 times 10 to the 3. Right. Divided by the area, which we know is this. So do all in one go on your calculator if you want to. I mean, this comes to something like 0.5011, isn't it? Something like that. That comes to that, look, meters squared. Okay, so that's the area. Let me scroll down there. Okay, so I'd put that in there. Force divided by area, that's the area. 0.011. This will give us the shear stress. It's going to be a big number. It comes out to be a funny number, 8.182. That's the answer, pascals. So the answer is that. Press E and G, you get 8.1. Confused with how many 8s? 8.1818 times 10 to the 6. If you press E and G in the calculator, engineering format, or because 10 to the 6 is mega, so you could say mega 2, perhaps. I'll leave it like that for now. Megapascals. All right. So there's nothing wrong with this answer. Nothing wrong with that answer. Nothing wrong with the answer. Just make sure you get the right numbers and the right decimal places. Okay, that's the shear stress. Shear stress. That's how much stress this thing's under. Okay, so that's part 1 done. And then the next one is shear strain. So we're going to find shear strain. Shear strain. That's the next part coming up. So the next part is shear strain. We've done shear stress. Let's get a different color. Let's go there. So strain, because a force will cause a stress will cause a strain. Okay, so we've done the shear stress, 8.18 megapascals. Okay, now we've got to do the shear strain. Okay, now we know that strain, the formula for strain, or a formula for strain, is change in length over original length. So change, delta L means delta, that's the Greek symbol there, triangle means delta, right? So delta L, all it means is change in something. So put change in length, right, over original, which you've seen before, or should have perhaps. Okay. So if we know the change in length and we know the length, we can find the strain. Now with shear stress, okay, the change, okay, is that 0.8, that sort of deformation there. Okay, so in our case, the change in length here is 0.8. Okay, and the length is going to be, it's not going to be the 200, it's not going to be the 55. Okay, because it's this 30. Okay, the higher something is, the more it's going to go on a squint. If you think about it, the higher the building, the taller the building, the more it's going to move in the wind. The taller the tree, the more it's going to move in the wind. So the length that determines how much the change is how high it is. Okay, so in our case, it's 30 mil. Okay, don't use this length, don't use this length. It's the height. Okay, so because it's a ratio, it's length over length, we can keep them both in millimeters. Okay, so strain is change in length, which we know is 0.8. And the original length, which is the height really, is 30. Okay, they're both in millimeters, which means we can use them. If you converted these to meters, you get the same answer. Okay, but it's easy for us just because they're millimeters, so we can use them. It's a length over length. If you want to convert 0.8 into meters and 30 into meters, you can do it, but you'll get the same answer. So all we're going to do is this, 0.8 divided by 30. On your calculator, that'll give you 0.026. No units, dim unit, no units, it's a ratio. Okay, that's the strain, done. Ready, Benny, happy days. So that's the strain, that's the stress. All you've got to make sure is that you get the size of the force correct, get the area correct, get it into meters, and then with the strain, make sure you use the height. Okay. So there we are. Any problems, let me know. That's it for now. Over and out. North Star.